normally you don't see the header, but if you could click on the sender and then if your email client there's a header, it's good to look at the header. What are all the information in the email header? And sometimes you could see this S MIME, okay, or at least MIME, M-I-M-E. MIME stands for multi-purpose internet mail extension. So what it means is, with S MIME or just with MIME, you could send any form of data like attachment, PowerPoint, video, audio, image, anything. With PGP, you can send only text messages. Okay, so the original, when they developed email in the early days, they initially targeted it to be used only for text communication. Okay? So PGP was developed a long time back, and even from a security point of view, you can use it only to secure text communication. So from that aspect at least, we can say SMIME is better. So you try to differentiate between the two standards, this could be a question. I have explained in detail the difference, various differences between them. So one key difference is PGP is used only for text communication, whereas SMIME is used for all sorts of data format. Okay? And also because of that, most of the web browsers, so all this mod plugin software, the PGP software or SMIME should be plugged into your browser. So when you open an email, that should run behind the scene and check quality of your email before it opens the email actually. Okay? So most of the browsers come pre-installed with SMIME software rather than PGP. Okay? So it's more commonly used and available. And also another thing is, as we go through this, very similar to what we have been doing, you will notice that PGP doesn't require you to use public key certificates. Okay? So what rather PGP does is, it lets the user to trust the other user. Okay? So if I want to use your public key, it's up to the receiver to decide whether to trust you or not. If the receiver trusts you, I can decrypt whatever you send using your public key. If I don't trust you, then you may want to send me your certificate. And your certificate need not be certified by a certifying authority. If a public key need not be certified by a certifying authority. It could be just certified by someone else whom you trust. So for example, if I want to open your email, right, I don't have your public key. So I really say I don't trust you, I don't know beforehand. So ideally, to be kind of safe, you have to, the receiver has to expect the sender to send its public key certificate, certified by the certifying authority, right? You see what I'm telling? The sender is sending to receiver, right? The receiver doesn't know the sender. So to be safe, on the safe side, what should be sent? The sender should send its public key certificate, right? Receiver. But since PGP doesn't require, and this should be from whom? The certifying authority should sign it. But since PGP doesn't require you to present the certificate signed by CA, the sender could send a public key certificate signed by another user, say A or B, whoever it is, a third party basically, whom the receiver trusts. It's just not a certifying authority, it could be someone whom the receiver trusts. But if this person is already compromised or something, then it could be forged. Okay, so it's not that secure. Okay, so PGP is not that secure, but it overcomes this requirement of having public key certificate. So that's their intention. They don't want people to always use certificates. So what they instead suggest is this web of trust. I think that's the name I have there, web of trust. So it could be kind of related, like the certificate model. The thing is, you trust someone, and then that person trusts someone, and then this person can get certified by him, certified by him, and so on. So they all need not be certifying authorities. It's just like all this interconnection. So this person recommends him, and he knows this person. So because of that, that person can get it certified, and so on. Okay. So it's all the users. So this is certified at the user level. The public keys are certified at the user level, not at the level of the certifying authority. So that's the key difference. Okay? It uses public keys, or it just requires the public keys to be certified only at the user level, not at the CA level. Okay? So that's the key difference.
Dr. May, which one Yahoo use?
Yahoo? I don't know. Most like I don't think Yahoo or any. It's up to you, the user. The browser has to be. You have to download and install it in your browser.
Would that prevent that from happening to me again if I did that?
You see, both parties have to have. So whoever communicates with you then has to have all the keys to open your email.
Oh, that's a downfall.
That's the real, yeah. You're not happy with Yahoo, I believe. Okay, so let's see PGP and then we'll see briefly about S-MIME. How does it do? And we have covered most of that already. So now we want to provide authentication here. And it looks like it also, the way we have done it, it can also provide integrity. The way I have that there. So you don't need to really remember this diagram. All you need to remember is this. How you write it in a format like this. Look at that, what I have there. The sender sends the message encrypted with the private key of the sender encrypting what? The hash value of the message. Okay. So to see that, this provides you authentication. Why? You sign with the private key of sender. So when you send it as it is, right? Of course, that is not a confidentiality right away. Of course, you can also zip it. So if you see, you can have it zip, compress. You know, zip means what? Compression, right? The reason they are doing compression is you are not just sending a message, you are computing this hash value, encrypting the private key and all those things. So that increases the message size a little bit, right? So in order to compensate for that, you are compressing the whole thing. You see the reason for compressing? This is what really wanted to send, the message alone. But you are attaching or appending to that the hash value encrypted with the private key. So that increases the message size. So to compensate for that, PGP uses compression. So you can compress the whole thing and send so that you kind of, what do you call it, at least think the message, the whole thing, the size of the whole thing will be almost the same as the message size. Okay? Clear? Now, let's look at the analysis. Does it provide you confidentiality? Anybody can decompress or uncompress, right? So how do you want to call it? Decompress, that's the way we call that, or uncompress, anything is fine with me. So anyone can uncompress it or decompress it and they can get to know this. So it doesn't provide you confidentiality, right? But it provides you authentication. Why? Again, like what I explained 2 minutes ago. This receiver can compute the hash value and decrypt this with the public key of the sender, right? As I said, you don't need to, because ideally, like using S-MIME, the sender has to send. If the receiver doesn't know the public key of the sender, the receiver should not ideally decrypt this, right? But PGP doesn't require you to send what? The public key certificate. So it assumes that the receiver knows the public key of the sender. Okay? And then, so what happens? So the receiver can decrypt the public key of the sender, extract the hash value, and what? You can compare them, right? And the two hash values should match. So since nobody else can sign, if somebody changes the message, right? So if somebody changes the message, because it is sent out in the open, isn't it? So someone who can decompress it can get the message, right? So they can change it to M prime, but can they change, or can they can compute the hash value of the corresponding message, but can they sign it with the private key of the sender? No, you cannot sign with the private key of the sender. So that provides you the authentication that it came from that sender. Okay? And because of that, nobody can change it. They can change it in the sense that they can change, but the hash value will not still match. They can change it to M prime and send as it is. The hash value of M prime will not be equal to what is inside that. So hash value of M, right? So the message will be corrupted, but the receiver can find it out. Okay? So in that way, you can say it is not guaranteeing you integrity, but the receiver can find out that it lost its integrity. So it's not that, see, integrity really becomes an issue if someone can change the message and the receiver cannot find it out. So that's when the problem is. But here someone can change it, but the receiver can still find out that the integrity of the message is lost. Okay, so because then the receiver is not going to accept the message. So the damage is not done. So when you change the integrity of the message, you really prefer the damage to be done. But this is still not good because you change the message and make the receiver drop the message, right? So this could cause what is called a denial of service attack. If you keep on doing that for every message that's being sent to the receiver, then the receiver is not going to really process any message, right? So that's kind of a denial of service. Isn't it? Yes.
The third person decrypt that hash. Is that?
Yeah, the third person can decrypt the.
Because he knows because the public is exposed, right?
Right.
So we can compute the hash.
Third person can get this, decrypt this, get the hash value, right? And he can compute the hash value of this. So like the receiver does, the third person can do that. But the third person wants to change the message, right? He could compute the hash value, but he cannot sign it with what? The private key of the sender. That's where the problem is. He cannot encrypt that to the private key of the sender. So all he could do is, he could change it, but send this as it is. But by doing that, what happens? The receiver can still find it out, the message got changed. So the integrity is lost, but the receiver can find it out. But still the problem is, if the malicious person can keep doing this for all messages that are being sent, the receiver is not going to process any message, so it's going to drop all of them. Right? So in that way, I said this is a denial of service issue. Okay? So the confidentiality is lost, the integrity is also lost, but it does provide you the authentication because of the signing of the private key. Okay? So like I asked in the quiz, the whole thing can be fixed by doing what? By encrypting, instead of just sending like this or sending the plain text, you can do what? This is what I told as the answer for the quiz, right? But in the quiz I told you should encrypt this with the public key of the receiver. If you encrypt the public key of the receiver, nobody can touch the inner portion because they have to decrypt with the private key of the receiver. Okay? So that's the thing. But in BGP here we don't care about confidentiality with just this model. So that's why we don't do the outer layer of encryption. So now how do we do just confidentiality? It may not provide you authentication. So let's see that model. So now with confidentiality we prefer to use, the reason why, again, why it's not, or they have not used that what I just said. Can anyone say? This is perfect, right? It provides you confidentiality also, isn't it? As I said just now. So why it's not recommended to use this strategy, even though it provides you confidentiality and integrity and authentication and integrity, all the three, right? Why you don't encrypt with the public key of the receiver? Not that. I remember the first class I did tell you that basic difference between symmetric and public key encryption, where you use them. You see, this is, you are encrypting a message with the public key, right? You don't do that normally because public key encryption is a lot of overhead. In the sense I told you, public key encryption is done using software, right? Like you do all this math, isn't it? You have to be implemented in a software program. It takes time.
So it's slow.
Slow. Whereas if you use symmetric key encryption, it is faster. All symmetric key encryption algorithms are implemented in hardware, most of them. So if you use symmetric key encryption to provide confidentiality, that's what we're going to see, it's more faster. So that's why we are going to use symmetric key encryption. Okay? Now, as I have written the differences for PGP here between PGP and SMIME, one other difference also is this. As you see, I have listed the names of the algorithms. The hashing algorithm, PGP requires you to use specific algorithms. Like there are several hashing algorithms, several public key encryption algorithms, several symmetric key algorithms, right? That are out there. PGP requires you to use certain things. Okay? So the hashing algorithm it wants you to use is this SHA hashing algorithm that is 1160-bit hash value. Okay? And the RSA is the public key encryption algorithm, and the zip algorithm is the compression algorithm. Like that, there are several other RAR and all those things, right? So out there. So PGP requires you to use only specific things. Now for confidentiality, the way it's going to do that is we have a secret key or a session key that is generated on the fly. On the fly means the sender generates a secret key, sends it to the receiver as part of the message. And a secret key is generated for every message because the sender is going to send it, right? So the sender generates a secret key for every message, encrypts that message with that secret key and sends it to the receiver. Alright? So what the sender does is it generates a secret key. It has to be sent, of course, secretly, right? So before that, the secret key is used for the encryption. So let me show it like this. The first part is the secret key AS, encrypting the message. Okay. Of course, the sender generates it right away. So the receiver has to know what is the secret key so that it can decrypt this, right? So the sender has to send the secret key securely. So for that, what you can do, encrypt the message with the secret key with the public key of the receiver and concatenate them. So if you send them together, the confidentiality is achieved. How? How does the receiver process this?
With the
You send
private
both
key.
of them like this. How does the receiver process this?
With the public key first, right?
I want to ultimately retrieve the message, right? I cannot touch this part because I don't know the secret key. The receiver doesn't know the secret key right away, right? So it has to decrypt this. So it has to decrypt this with its private key. And nobody except the receiver knows the private key.
So you got public right there, though.
This is what I send.
Okay.
When I send, I encrypt with the public key of the receiver. So only the receiver can decrypt with his private key. So the receiver has to attempt to decrypt this portion, right? So nobody else can do this. So this has to be decrypted, extract the secret key, and then do this decryption. That provides you confidentiality. Okay? It doesn't provide you authentication. Why? Anyone can come up with this. Anyone can spoof as the real sender, as we did discuss, encrypt the public key of the receiver, generate a secret key of their choice or whatever, encrypt that to the public key of the receiver and send it, right? So the send receiver cannot verify that it came from the sender. How does the previous scheme guarantees you that? Because the hash values, if the hash values have to match, right? The hash values will match. If someone, say, made up the message, right? If someone made up the message, they have to encrypt that message with what?
The secret key.
With their secret key, with their public, private key, right? The previous key. But that will be the bad guy or S prime. So, but the receiver thinks it's getting the message from whom? S, right? It doesn't even know the public key of S prime. So the receiver will try to decrypt this with the public key of the original sender S. So when you use the wrong key to decrypt, you will not be able to decrypt this as it is. You will get some junk value, right? So the hash values will not match. When you compute the hash value of the message you got and the hash value of whatever you are getting out of the decryption process, it won't match. Because they are not using the right key to decrypt. Because the receiver thinks it's getting it from S, the original sender, but the bad guy has to, if at all he wants to send like this, he has to encrypt with his own private key because he doesn't know the private key of the original sender. Right? So it won't be successful for the attacker to do this to affect the what? Say authentication. So it has the sender, the receiver can make sure that it came from the original sender. Whereas here, there's no way to verify that because again, as I said, you can do spoofing, so you can make the message to come from a particular sender, and there's no way, nowhere here is signed with the private key of the sender. So in order to provide authentication, you have to sign with the private key of the sender. It's like visual signature. Okay? So there's no way you sign with your private key. So this model provides you only confidentiality. It's good because it generates a secret key on the fly and sends a secret key right away. So if you want to send another message, it again generates a new secret key. Okay, so you don't use one secret key for all messages. So secret keys are generated on the fly and they are sent along with the message. So that's a good strategy. Okay, and I'm thinking of a project on this PGP where it's not programming, it's just doing some sequence of steps, but I'm not sure the way. But the way you generate the secret key is you run a program, and when you're running the program, it will require you to keep typing on a keyboard, okay, and do some background work like download a file or something. Why? Because you know, like when we look at random number generator, right, you need a seed value for that, right? So when the secret key is generated on the fly means there has to be some kind of random number generator, the kind of program that generates the secret key, right? And the seed for that secret key generator program depends on what key characters you're typing in a keyboard, okay, some random characters, as well as what's the system load and what else is running in the program system and things like that. So it's very interesting software. So it requires you to do something in order to generate the secret key. And you could do anything you want, just random things, not the things. Okay? So how to achieve both? How to achieve confidentiality and authentication? Just put these two things together. And that's what I have done here. So generate the secret key, encrypt the public key of the receiver. It's the same as this previous step. And see, this is what we did, the compression of the message as well as the hash value signed. This inner thing is what we did for authentication, right? So now encrypt the whole thing with your secret key. And this is what I said, instead of that secret key, I said you can use the public key of the receiver, right? But I said we don't prefer to encrypt the whole message with the public key of the receiver. It's slow. So instead of public key of the receiver, use what? The secret key. Okay, so encrypt the whole thing with your secret key. Of course, you can zip it and then encrypt it, but you get the idea, right? So when you encrypt the whole thing with the secret key, the message is confidential. Nobody can look at it.
So it's gonna ask for the hash values before it does the rest of it.
Right. So let's look at that. What is the order the receiver is going to extract the information? So this is the whole message, right? But you understood what you are doing here, isn't it? This, as it is providing you just authentication. When you encrypt this with the public key of the receiver, nobody else can decrypt that, right? That gives you confidentiality. But as I said, you don't normally use the public key of the receiver to encrypt this because it's time consuming. Okay? If you encrypt the public key of the receiver, everything is done. It provides you authentication, provides you confidentiality, everything. But it's time consuming, so that's why you prefer to encrypt that with the secret key. But the secret key is not known to the receiver. So that's why you have to send the secret key along with the whole thing. And that's what we are doing in the second part. The secret key is sent along with the whole thing. but you have to encrypt the secret key with the public key of the receiver so that the receiver can decrypt with its private key, get the secret key, and then go to this part, right? So let's look at that. What order you will be decrypting? You're sending this along with this, right? So the big thing, encrypt the secret, encrypt the secret key with the public key of the receiver. So the receiver gets this. What order it will decrypt the whole thing? Can the receiver touch this first part? No, because it has to be decrypted with the secret key, right? So it has to know the secret key.
So you have to do the secret key first.
Right, so you have to decrypt this to get the secret key. So when I ask you to write the order, which I could ask you in the exam, write this thing and write the order in which you decrypt. Okay? So use the private key of the receiver to decrypt, extract the secret key, and then do what? And then decrypt this with your secret key. Once you decrypt this, you get the inner portion, right? So what would you do then?
Encrypt the hash value.
You decrypt this thing, decrypt this with the public key of the sender, get the hash value, right? The encrypted hash value. And then you run your hashing algorithm like SHA, whatever it prescribes, compute the hash value here, and compare the two hash values. The two hash values should match. Of course, you have to decompose too, so that may be one intermediate step. So after you decrypt this, you get the compressed form, right? So you have to decrypt first, not decrypt, decompress first to get the inner portion. So, understand what I'm telling?
So decompress press will be 3.
Huh?
So
So
decompress
will be a third step. Good. So decrypt with your secret key, get the compressed whole thing in a compressed format, decompress this to get the inner thing, and then compute, extract, do this decryption with the public center, then compute the hash value, both of them should match. Right? It's a logical step, and that's what those pictures there describe tell you. So you can use also those pictures to see what order you are really doing all these things. But you don't need to memorize the figures, you just need to know this equation, the kind of statement. Okay? So we'll stop here and move on to S-MIME and